Designing a reinforcement learning algorithm in system with a sparse reward, which means that the environment doesn't provide a lot of information to the agent throughout the training, is a challenging task. In this video, I will deep dive into the learning process to design an RL algorithm that can effectively solve this challenge. We will use the algorithm ACER, which is actor critic with replay buffer. I will try to talk about the different challenges that you might occur and what we can do in order to solve them. Welcome everyone to your channel, AI Fun Fact for All. For those of you who are new to the channel, my name is Pedram Agand. I'm a PhD student in computer science, and this channel we talk about AI and machine learning in our everyday life. As we mentioned in this video, I'm going to talk about a little bit more AI concepts, which is designing a RL algorithm. Reinforcement learning is an effective algorithm to design an agent that do a specific task without requiring to have a lot of labeled data. So as an example, when we are designing an autonomous driving, you can try to mimic the behavior of the previous drivers, but this so-called the imitation learning cannot be very effective because there might be some situation that we haven't seen in the environment and our dataset. So in those cases, the supervised learning and unsupervised learning can actually fail. So we require some other algorithm which try to learn a policy or a decision-making unit, which try to actually learn something out of the interaction with the environment and try to come up with the algorithm that can decide what we need to do in specific occasions. The only information that we get from the environment is the reward, which basically means that is the action that we did was a good action, or we are gonna get penalized if it was not a good action. Reinforcement learning is actually among a lot of other algorithms. For example, even in the design process of ChatGPT or other large language model, we require some RLHF, reinforcement learning with human feedback, which try to do a little bit of alignment, which means that we get the response of this large language model to be a little bit aligned to what we expect to hear. So what makes this problem challenging is that if the only thing that we receive from the environment, which is the reward, is very sparse, which means that we rarely receive some informative feedback from the environment. So in those cases, the problem of the R algorithm become even more challenging. And why is that? Because when we are doing the interaction, we don't receive any intermediate reward, or if we do, it's not very informative, and we just need to wait so long until at some point we receive a very high positive reward or very low positive reward. The environment that we choose for this problem is the squid hunt, which means that we have an agent that is trying to avoid the walls that is passing by going up or down, and also try to shoot the squid. So if they shoot the squid and was successful, they get a positive reward, and if they hit the wall, they will get a negative reward. This squid hunt game is actually not very a strategic game because you don't need to care too much about the gain or reward that you will get at the end compared to the one that you get intermediate reward. And the reason is you just need to focus on the current state and try to avoid the wall, obviously, at the first time. And also, if you see any squid, you try to hit it with the shooting. And basically you don't need to think or do something bad at the current time in order to get something better in future, and for that reason it doesn't require a very large gamma. So for that reason it's going to be a simpler problem. However, there is still a problem because of this sparsity, which we will go over what are the things that we can do to handle it. In this video I will only talk about the concepts and the problems that you might occur and how you can solve them, kind of like a conceptual case. If you guys enjoy the video, let me know in the comments, and I will create another video which I will talk about the implementation of the code. We will go over the code and a different round of implementation. The first question that we have is that why should we choose ACER, or actor critic with experience buffer? So the reason is actor critic is very helpful in the scenario when we want to have the update of the actor, which do as a policy update, and also critic, which do act as a network that updates the Q value. We're gonna have the actor critic method because it has the both potential of the policy gradient and also deep Q learning. So if we want to have the benefit of both, we can choose an actor critic which try to consider both of them at the same time. But there is also a downside of it, which is since it requires more structure, it requires more designing of hyperparameters, and also there are so many things that can go wrong, and that's why we actually choose this algorithm. So we know that, okay, so if this happens, what we need to do, and so on. And in addition, we also choose a replay buffer. So replay buffer plays an important role in on policy algorithm, and the reason is we want to be a little bit more effective in our data efficiency. So RL is very data inefficient because we require to do a lot of interaction in order to get something useful from the data. But if we do experience replay, what will happen is that we try to track these interactions and then reuse them again and again based on the batch that we sample from them. So it's kind of going to be not the traction that comes and we just throw them away. We will have them and we can reuse them again, and then there's a constant size for it. So the ones that actually happened a long time ago is going to eventually fade it and throw away because it is an on policy, and we want to go based on the latest policy that we are training on. The ones that was very original of our training is not useful that much. But at the same time, we need to make sure that since it is an on policy approach, we need to make sure that it doesn't go, the learning rate of it is not too high, so it just go to a local minimum, and we want it to experience as much as exploration. Otherwise, it will just try to be too confident in some policy in the earliest stage, and obviously it wouldn't explore all of the different capabilities. So that's the problem of on policy. We will talk about how we can even make this replay buffer better and more effective. The next question is about the challenges that we might encounter when we are training the algorithm. These challenges can be the problem of oscillation of the reward, it can be the problem of exploration versus exploitation, and also the policy collapse. So what we need to do is that we need to see that if each of these happens, first of all, what are them and how we can detect them, and if we detect, what can we do in order to solve them. This is what we are going to cover later in this video. The other question that we might have is basically how to do the hyperparameter tuning. So hyperparameter is actually very important in an RL algorithm, and we might have a fully functional RL algorithm that might not work well because the poorly chosen hyperparameter. So basically the RL algorithm actually is very sensitive to hyperparameter. The hyperparameter can vary a lot, and for the ACER algorithm, the number of them can be, for example, the gamma, which is basically the duration of considering how long in future do you want to include, or farsightedness. And then we have entropy coefficient. We have the entropy coefficient is when we want our basically policy to explore, and then we have have the buffer size, which means that what is the fixed size of the buffer. Can it be too large? Can it be too small? What will be the issue from them? As I mentioned before, we are using ACER, which is active critical replay buffer, and replay buffer help us to be more data efficient. But just having this replay buffer somewhere still in there is not going to be a very informative. How we can make it more useful is by making it priority. So how you can create a priority experience replay is that if you hand select or somehow let the replay buffer know that, for example, this specific transition has more informative information and this transition can actually be forgotten very fast. So what do we mean by that? Let's say you have a sparse reward in our case. When we are storing the transition, there are so many transitions that get a very small, non-very informative or not at all any reward. We are gonna store them. As we add more data into it, the one that was added first is going to be forgotten, right? So we are going to remember the last number of the buffer size, but what will happen is that this is going to be time dependent. But at the same time, if some of these transition, and we were lucky and we saw some transition early in our training that was very informative and has those sparse reward, we don't want to just throw them away. So it's a good idea that we have some prioritized experience replay. So how do we do that? If we detect that some a transition have a higher reward, we want to store them somewhere and treat them a little bit different compared to others. So you cannot just say that, oh, I want to have them forever, because still you're gonna later on get to some other transitions that is better. So we still want to have the time dependency, but we don't want to treat it same as the other one. And this is actually true not just for the high reward, also for the very negative reward. So if something happened and there was a very huge punishment, we also want to remember that. So these are the key moments. We want to somehow be able to remember these key moments higher. So how you can do that? There's a naive approach. What you can do is that you're gonna say that I'm gonna compare and store something, for example, let's say just for the high reward, I'm gonna say that, okay, if this value of transition is higher than the average of my buffer in terms of reward, I'm gonna store it. If it is not, I'm not gonna store it. So what will happen is that then in this situation, you are too much learning the concept of high reward and you don't have any information about the other cases or negative reward. So we also don't want that. So we also want to have the basic approaches, the basic, for example, reward, and more recent one, because if we just do it based on if it get better, the replay buffer actually updated very rarely. It doesn't update very much. So this is not also good. So we want to have a solution that, for example, 80% of our replay buffer is actually the usual replay buffer that updates like a queue. The new come in and the previous one is gonna throw away, and then 20% of them, the 10% is gonna be saving the high reward, and the other 10% is gonna remember the negative reward. So we shouldn't just remember the positive, we shouldn't just remember the negative, we need to remember those ones, both of them. And then those ones can actually be the top, for example, reward regions, but also have the queue, so the top latest queue regions. And then we're gonna work in that case. And when we are sampling from the buffer, we make sure that, like, for example, 10% of our sample are actually samples from these priority. So the key or what we will get out of this is that we are gonna indirectly let the buffer know that these experiences are actually convey more information, and we shouldn't just let them go very easily. The problem that you might encounter is policy collapse. So first, what is it? Policy collapse happens when your policy become confident, too much confident that it doesn't change. Then what will happen? The log of that probability will become 0. So the probability will become 1. It's going to be too much confident in taking some actions, and then at the same time your log probability is going to be 0, and then obviously your error for the action of the actor and also the exploration, both of them, since they have this log p, is going to be 0. So this is actually good if it was later and down the road, but it usually happens in very early stages because the agent is stuck in local minimum. When it is stuck in local minimum, it will try to just remember and get too much confident about this, and the log p gonna be equal to 0, and then you basically don't learn, don't try to do more exploration. So that is what's the issues. So how we can promote the exploration in here? So obviously the first thing is that we don't want to stuck in the local minimum. Obviously the first thing is that we decrease the value of learning rate. But at the same time, we don't want to make it very small because it's going to take too long. So it's good idea to use a learning rate scheduler, which at the very beginning is larger, but at some time it actually decays. The other thing is basically the entropy coefficient. So if we increase the entropy coefficient, then we want the agent, we're gonna give some incentive to a agent to actually explore new things, and we are going to add it as our basically in the form of our cost function. So we want to maximize this exploration. So have these things maximized is going to help us to overcome this problem of being too much confidence, and we kind of give some incentive for exploring more and more. The other problem that you might encounter is basically the oscillation of the reward. So this is actually very frustrating. You will try to learn some reward, but then after that you will oscillate around it, so you don't learn something more than that. So this can be resulting exactly again stocking in local minimum, which can happen very commonly. But what we can do about it, there are so many things that we can apply. The first thing is that when we see that the environment is actually oscillating about a certain rebar, we need to somehow again more incentivize the exploration. So if we explore more often by increasing the entropy coefficient, we make sure that we don't stuck in that local minimum, or reducing our learning rate, and some other facts that we can do. There are also some other approaches that use in supervised learning, such as regularization. So we can add regularization to our loss function, both of the Q value for the acritic and actor. The other thing would be the discount factor. So if we have our discount factor too low, because we said that it's not defining it strategically, but at the same time, if it is too low, like 0.8, then what will happen is that it will look too much at the current reward and the reward that it will get right now, rather than looking at the Q value, because each time how we are updating our target Q is based on the Bellman equation, which is one step TD. So if we have this gamma very small, then the value of the Q does not have a lot of effect on calculating the current value of the previous step. So for that cases, the Q is not going to be that much important. So if we increase the gamma, even though that we know it's not very far-sighted, but increasing that will actually incorporate the previous value of the Q and try to update the Q more often, and then let us get free from the local minimum by just getting some intermediate rewards. The other problem is by having a replay buffer that contains very similar situation. So that is what we don't want. We don't want our replay buffer to be just the top 10% or just the worst 10%. But even though that we try not to have it in our prioritized queue, still there might be some situation that we might encounter that. So in order to avoid this, we need to increase our size of replay buffer. So the replay buffer cannot be too small, because if it is too small, then it can only contain some certain of experience, and it will avoid generalizability and having variety of experience. So when we are getting batch, we get a variety of generalization. But at the same time, it cannot also be too large, because if it is too large, then in the very beginning we are waiting too long for the agent in order to update, because we can only update our policy and our queue when we have enough data in our replay buffer. So if we waited too long, we are going to collect a lot of bad data, because it's going to be completely random, and then it's not going to be very efficient. So if we waited too long at the same time, it's not also good. So a happy medium would be definitely suggested. The most important thing that you can do when you see the oscillation in the reward is actually changing the reward itself. So by tweaking the reward in a mechanism called the reward shaping, you can actually avoid having some of the reward that are not useful for you. So I will give you some example. Let's say you have a very sparse reward that you need to wait too long to get some reward at the very end. You can somehow create something called a to-go reward, and if you do that and you try to back propagate and somehow get some reward for the intermediate steps, then that's going to be hugely beneficial. The other thing that you can do is the value of the reward itself. So if the value of the reward is too high, so for example it is like around 0.01, and then suddenly it becomes 5 or -5. So these two cases will change the value of the update for the policy too large. So what will happen is that most of the time, majority of the time, you will get a value of 0.01. It will try to update it, but then some transition you get a value of 5. But then you already know that this transition is actually very important. But if you actually included inside your update, the value of 5 is around 500 times more than your normal value, and this 500 times will create some instability and numerical instability for you. So then in order to avoid that, you might want to reduce your learning it, but then reducing it might take you a long time to actually reach it. So this is not the best approach. The best approach is reward shaping, which means that you try to clip your reward to have some value that makes sense, not a value that is too large result in a very huge updates. In order to solve the problem of divergence, there are other approaches like multi-thread data and also multi-agent. So these approaches try to get multiple interaction with the environment and try to solve that problem that we talked about, that like our experience replay is going to be contain only one notion of transition, and then we don't learn new things. How it works is that on the multi-agent, we're gonna have multi-separate agent that is working with separate environment, and then after a while we asynchronously average the value of their weight to a weight and distribute among them. This is one way, but obviously it requires more training, it requires more resources and so on. And then we also have multi-thread data, which means that there's only one agent, but asynchronously it will have multi-thread or multi-worker that gets the data from the environment, and then this data get from the environment, there is a higher chance that we get good transition from them and we don't stuck in one value. Also, in order to avoid this, it's also suggested that you have even in the policy to be random, but again that might, since it is on policy, it might again like become exploited. So it is a good idea to have an epsilon greedy in there as well. So even though that you are choosing something randomly, you also put a little bit more epsilon randomness into it, and you don't choose it just based on the multinomial or based on the probability distribution of that value. And there you have it, guys. We went over different problems that can occur for a sparse bar. I talk about the common challenges on how we can address them. It was a little bit technical. If you enjoy video like this that goes technical, make sure to watch this video that I created before about event sequence learning with the transformer. If you enjoyed the video, make sure to like it, and more importantly, subscribe to the channel. Let me know in the comment what do you want me to cover in the next video. Thank you, and see you until the next one.